So these are the examples how we can find the probability. Now our question is, how can we generate a set of random numbers? And why I use the term pseudo-random numbers? Random numbers are useful in analysis of stochastic systems and other systems, and also in the signal processing analysis. So suppose there is a curve. If you want to get a correlated curve, you have to add random numbers to it, as I did earlier in the example. So how to generate random numbers? Real random numbers can be obtained by electronic devices. These are real random numbers. There are certain limitations in using real random numbers. One is the random numbers generated in that way by electronic devices cannot be repeated. So the experiment, if you are trying to do by simulation, cannot be repeated. So that is not a good way to generate random numbers. The other one is electronic device generated random numbers are only for uniform distributions or uniform distributions only. They cannot generate other kind of distributed signals. So we are trying to think about generating random numbers by computers. And there are certain algorithms to do this. And this kind of random numbers are generated based on a seed. You can select a seed and using a mathematical formula, and you can generate a sequence. And this sequence usually satisfies statistics properties of the signals. And if the themes are the same, then if you use the same mathematical method, you will generate the same sequence. So this kind of signals are repeatable. If you want to get the same sequence of random numbers, you can generate the random number with the same seed. If you are using a different seed, then of course you can obtain different sets of random numbers. Because this kind of random numbers are generated by mathematical formulas rather than electronic devices, we call it pseudo-random numbers, because it is not real random numbers. However, it does satisfy certain properties you require. And this is one advantage of pseudo-random number generator is that they are repeatable. So you can do repeated experiments. And the other one is you can generate certain random numbers which satisfy required distribution. For instance, you can generate a random number satisfying gamma distribution or Rayleigh distribution or chi-square distribution with certain commands in Matlab. And you can use a function name and a statistic toolbox like this. For instance, if you want to generate a beta distribution, then the function you have to use is beta R and D. Use this function, you can generate beta distribution function. Now let's go back to the table again. There are keywords and parameters and keywords. Apart from this, we have suffixes for the functions. If you want to generate a random number, for instance, if you want to generate a gamma distribution random number, the function you need to use is gamma R and D to build the function. You can compose different function names to do the similar thing. And you have to specify the properties of gamma parameters A and lambda. this is the probability density function of the distribution. Now we have A and lambda as the key parameters. So you can generate gamma distributions in this way. So now I will make a demonstration here. I want to generate 30,000 points of random numbers satisfying a Rayleigh distribution. So this is the signal random number generator problem. And also I want to verify the result of the distribution generated and see whether it is very close to the theoretical Rayleigh distribution. So there are two purposes. One is to generate, the other one is to verify the result. How can we do that? For the first problem, we can generate the Rayleigh distribution points by the use of a command like this. And then, for the first command, I can generate a p vector. And then, for a certain area, for a certain axis, I can divide the axis by several bins or cells. I can divide the original axis in several bins and check for each element of P to see which small bin it falls into. For each value of P, we have to do this. And we have to accumulate for each bin the number of points in P fall into that interval, or into that bin, so we can roughly draw the distribution vectors. So this is one way to verify distribution of the random numbers generated. And also we can draw the theoretical distribution of Rayleigh distribution, and we can compare whether the two results are close. If they are close, we say that the signals generated are quite good for Rayleigh distribution. If they are not close, we will say that the result is wrong. For the numbers generated like this, we can see that the histogram of the blue ones are quite close to the theoretical curve. So we say that the signals generated are very good for the original problem. There might be some errors like this, but you cannot expect that random distributed data exactly the same as theoretical one. So this one could be effective in real applications. Here I made the verification for the certain distribution. Actually, if you do experiment yourself, I don't think it is necessary to do the verification, because the signal random number generators are good enough for this kind of applications. So I did the verification here just to show that we can get good distributions from the functions. It is not necessarily in real applications. So that's about the distributions and random number generators. Now let's consider the statistics of the random